Listeners, I am Pawan Kumar, Assistant Professor of Mathematics, School of Sciences, IGNOU. Today we will discuss Introduction to Limits of Real Valued Functions 2. In earlier session we have defined that limit informally as means that the difference between fx and L can be made arbitrarily small by taking x sufficiently close but different to C. Then it means that fx approaches to L as x approaches to C. Now we will come to the formal definition. So before coming to that, we will use two Greek letters epsilon and delta to represent arbitrary small numbers. So we have defined that limit x tends to C, fx equals to L. It means that for the difference between fx and L can be made as small as possible by taking x sufficiently close to C. Here we use the two words fx as small as possible, and the word sufficiently close. So we will, to represent these words, we use two Greek letters epsilon and delta. You know that how to represent the difference between two numbers. So fx and L are two real numbers, so their difference can be represented as mod fx minus L. So this difference is small. It means that mod fx minus L is less than epsilon, and x is sufficiently close to C means x minus C is less than delta, and if x is not equal to C, we will take this difference to be positive. Note that x minus C is less than delta means x minus C lies between minus delta and delta, or x lies between C minus delta and C plus delta. But if we take here this difference to be greater than 0, then this means that here x is not equal to 0. So this represents the open interval C minus delta to C plus delta, excluding the point C. If you represent this on real line, it means that if this point is C and this is C minus delta and this is C plus delta, then excluding this, all these numbers form this interval. Similarly here, mod fx minus L is less than epsilon. It means that fx lies between L minus epsilon and L plus epsilon. Now let us define, using these notations, the limit so we can now give the formal definition. So to say that limit x tends to c fx equal to L, this means that for each epsilon greater than 0 there exists some delta greater than 0 such that zero less than x minus c less than delta implies mod fx minus L less than epsilon. So this means that when x is, for each epsilon greater than 0, we will find some delta greater than 0 such that when mod x minus c is between 0 and delta, then fx minus L is strictly less than epsilon. Choice of epsilon depends on us. We can choose epsilon as small as possible, however it should be positive. Then corresponding to that epsilon, we will certainly find at least one delta that will satisfy this condition. If we see geometrically, so if this is the graph of the function f and let L is this point and let C be this point, we assume that function may not be defined at this point C. So, and L is the limit of f at the point C. So let us choose some epsilon greater than 0. Let us choose some epsilon greater than 0. Then this number is, suppose, L plus epsilon, and this is L minus epsilon. Then corresponding to this epsilon, if you draw straight lines, and we will get some delta here, that this is C minus delta and this is C plus delta, such that if x belongs to in this interval, then all the fx will belong to in this interval. And now when epsilon is very small in size, or when it reduces, then this strip size reduces, and this forces the delta to reduce towards 0. So when epsilon tends to 0, delta also tends to 0. Then when delta is very close to 0, it means that x is reaching to c. Then only this difference can be less than very close to 0. So when x is reaching to c, then fx is reaching to L. Okay. Now let's take some example here. Consider the example limit x tends to 3, 2x minus 5. Graphically and numerically it is clear that the limit is 1. We can see that if you just put x equal to 3, you will get 1. Now let's see the definition to prove it. So to find a delta greater than 0 such that 0 less than mod x minus 3 less than delta implies mod 2x minus 5 minus 1 less than epsilon, and this happens true if and only if 2 into x minus 3 mod less than epsilon, if and only if mod x minus 3 less than epsilon by 2. So we can see that if we choose delta equals to epsilon by 2, then our job is done. Now let us verify whether this delta works or not. So 0 less than x minus 3 mod x minus 3 less than delta implies mod x minus 3 less than epsilon by 2, because delta is equal to epsilon by 2, which implies mod 2 into x minus 3 is less than epsilon, which implies mod 2x minus 6 is less than epsilon, implies mod 2x minus 5 minus 1 is less than epsilon. So which clearly satisfy the definition. Hence the function 2x minus 5 has limit 1 as x tends to 3. Now you focus on the value of delta, which is given to be epsilon by 2. If you take different values of epsilon, we will get different values of delta as shown in the table. When epsilon is 0.01, delta is 0.005. When epsilon is 0.001, delta is 0.005. When epsilon is very small, that is very close to 0, then delta is also very close to 0. It is then, since epsilon is arbitrary, we can take smaller and smaller values of epsilon, which results in successively smaller and smaller values of delta. So this is the graph of the function. Here we are finding the limit at the point 3. So as seen in the graph, when we choose epsilon, some epsilon, the strip shows that when all the values between 3 minus delta and 3 plus delta except 3 forces that fx lies between 1 minus epsilon to 1 plus epsilon. And now if the epsilon is reduced, then this results in reduction of delta, and which finally says that as epsilon tends to 0, delta also tends to 0. So then the statement mod 0 less than mod x minus c less than delta implies mod fx minus L less than epsilon, which means that mod x minus c tends to 0. That is, the difference between x minus c tends to 0 implies the difference between fx and L tends to 0, and it means that when x tends to c, fx also tends to L. That is what a limit means. Now let's take some other example using the definition, so that limit x tends to 9, x square minus 1 equals to 80. Solution: here fx is to be given x square minus 1, and the point c is 9, and the limit L is 80. We have to prove this. So first we choose some epsilon positive, and we have to find a delta positive such that if the difference between x minus c is less than delta and greater than 0, then the difference between fx and L is less than epsilon. That is 0 less than mod x minus 9 less than delta implies mod x square minus 1 minus 80 less than epsilon, which is true if and only if x square minus mod x square minus 81 is less than epsilon, which is true if and only if mod x plus 9 into mod x minus 9 is less than epsilon. Now since we need one such delta, so we can take any restriction on delta. Suppose we take delta less than 1, then 0 less than mod x minus 9 less than delta implies mod x minus 9 less than 1, and then the factor x plus 9 has the upper bound, which is 19. It can be written as mod x plus 9 equal to mod x minus 9 plus 18. Now using the triangle inequality, this is less than or equal to mod x minus 9 plus 18, which is less than 19. So now see the statement 1, we get 0 less than mod x minus 9 less than delta implies 19 into mod x minus 9 is less than epsilon, which further implies mod x minus 9 is less than epsilon by 19. So this suggests that delta should be less than epsilon by 19. Now we have also taken that delta is less than 1, so we will take delta minimum of 1 and epsilon upon 19. Now let's verify whether this delta works or not. So now we will give the formal proof. Let epsilon greater than 0 be given. We have found delta equals to minimum of 1 and epsilon upon 19 such that 0 less than mod x minus 9 less than delta implies mod x square minus 1 minus 80 equal to mod x square minus 81 equal to mod x plus 9 into mod x minus 9, which is less than 19 delta and which is less than epsilon. So this clearly satisfies the definition. Hence we have proved that the limit x tends to 9, x square minus 1 equals to 80. Now there is important fact about the definition. You might be thinking that why we take epsilon first and find delta corresponding to epsilon. Why can't we take vice versa? Suppose what happens if you assume that delta is given and we have to find epsilon, and suppose the definition now is to say limit x tends to c f x equal to L means for each delta greater than 0 there exists an epsilon greater than 0 such that 0 less than mod x minus c less than delta implies mod fx minus L less than epsilon. Let's analyze this definition. Suppose you are given a delta and you have found some epsilon corresponding to the delta. Then we can see all the epsilons which are greater than this epsilon will also work, and these may not depend on delta. If we force delta towards 0, then x tends to 0, but fx may not tend to L. So this is not a valid definition. Now let us come to one-sided limits. Let us define this. First we will define the left hand limit. We denote it as limit x tends to c minus fx equals to L, which means for each given epsilon greater than 0 there exists a delta greater than 0 such that c minus delta less than x less than c implies mod fx minus L is less than epsilon. Okay, let us take in the definition of limit we are using that when x lies between c minus delta and c plus delta, then fx lies between L minus epsilon and L plus epsilon. This is what we use when we define the limit x tends to c, fx equals to L. But now we are defining the left hand limit at the point c. So if this is the function and this point is, suppose this point is c, and so so x is tending to c from left hand side. So we will consider only the interval c minus delta less than x less than c, and then fx tends to L. So now if we take some epsilon greater than 0 such that this point is L plus epsilon, this is L minus epsilon, then correspondingly we will find a delta such that if we find this interval corresponding to this interval, we find this interval such that if x lies between this interval, then all the values of f lies between L minus epsilon and L plus epsilon. So this means that when x lies between c minus delta and c, then fx lies between L minus epsilon and L plus epsilon, and this is denoted as limit x tends to c minus fx equals to L, and we call it the left hand limit of fx at the point c. Similarly, we can define the right hand limit of fx at the point c. So we denote it as limit x tends to c plus fx equals to m. It means that for each given epsilon greater than 0, there exists a delta greater than 0 such that c is less than x is less than c plus delta, implies mod fx minus m is less than epsilon. Now if the left hand limit and right hand limit both are equal, then the limit x tends to c fx exists and its common value is L. Now let's take some example. We will prove these limits using the definition. So prove the following limits using the definition. Limit x tends to 1 minus fx equals to 1 equal to limit x tends to 1 plus fx, where fx is x plus mod x minus 1. So first let's prove the left hand limit, which is 1. So let epsilon greater than 0 be given. To find a delta greater than 0 such that 1 minus delta less than x less than 1 implies mod fx minus 1 less than epsilon, if and only if mod x plus, now we substitute the value of fx here, so x plus mod x minus 1 is less than epsilon, which is true if and only if mod x minus x plus 1 minus 1 is less than 0 epsilon, which is true if and only if 0 is less than epsilon, but we have chosen that epsilon to be positive number, so this is always true. So now we choose any positive delta that will serve the purpose. Similarly, the other limit can be proved. Now we have a special theorem. This is known as squeeze theorem, which says that let f, g and h be functions such that gx is less than equal to fx, which is less than equal to hx, for all x near c except at x equal to c, and further limit x tends to c gx equal to limit x tends to c hx equal to L, then the limit x tends to c fx equal to L. That means that when f is lying between g and h and both g and h are approaching to L, then f will also approach to L. Let's take an application of this theorem. Suppose if we want to evaluate the limit x tends to 0 x sine 1 upon x. To evaluate this, we will use a squeeze theorem. First, you note that sine 1 upon x lies between -1 and 1 for all non-zero x. We are excluding the point 0 because sine 1 upon x is not defined at 0. Now, if you see that if you multiply mod x in the inequality, we will see that x sine 1 upon x lies between minus mod x and mod x for all non-zero x. So here fx is x sine 1 upon x, gx is minus mod x, and hx is mod x. So limit x tends to 0 gx equal to limit x tends to 0 minus mod x equal to 0. Both the limits are 0, hence the function x sine 1 upon x also has the limit 0 by squeeze theorem. Now, till now we have defined the limits of functions at finite points, and limits are also finite values, but in many examples when function tends to infinity, then we call those limits infinite limits. Let us define them properly. To say limit x tends to c fx equal to infinity, we mean that for each positive m there exists some delta greater than 0 such that if 0 less than mod x minus c less than delta, then fx is greater than m. That means if you see the graph here, you just take some positive number m, and corresponding to this number we will find a delta greater than 0 such that if all the x lies in the interval c minus delta to c plus delta except c, then fx are greater than m for those x. Let us take some let's consider this figure. Here fx is tending to infinity as x tends to c. So let us choose first m, then corresponding to this m we get the interval c minus delta to c plus delta such that all the values of fx are greater than m for values of x lying between c minus delta and c plus delta. Now if you increase the size of m, let us take a bigger number m dash, then corresponding to m dash we get delta dash such that if all the x except c lies in the interval x minus c minus delta to c plus delta dash, then fx lies above m dash. And if we take larger and larger values of m, we get smaller and smaller values of delta. So it means that when m is getting larger and delta is getting smaller, so when x is tending to c, fx is tending to infinity. Now to say limit x tends to c, fx equals to minus infinity, we mean that for each m greater than 0, there exists a delta greater than 0 such that when mod x minus c is between 0 and delta, then fx is less than minus m. So in this case, the function tends to minus infinity when x tends to c. So let us take some m positive number, then minus m is negative number as shown in the figure. So corresponding to this m, we get a delta such that if x lies in the interval c minus delta to c plus delta excluding c, then fx's are below minus m. So when if you take larger value of m, that is more negative value of m, then we get a smaller value of delta. And finally, when delta m tends to infinity, then minus m tends to minus infinity and delta tends to 0. So when x tends to c, fx tends to minus infinity. We can understand it through this example. We are probing the limit x tends to 3, 1 upon x minus 3 whole square equal to infinity. So first we choose a number m greater than 0, and we have to find a delta greater than 0 such that when mod x minus c lies between 0 and delta, then fx is greater than m. That is, now we substitute the value of c and fx here, we get 0 less than mod x minus c, mod x minus 3 less than delta implies 1 upon x minus 3 whole square greater than m, and this can happen only if 1 upon mod x minus 3 is greater than the square root m, and which is true if and only if mod x minus 3 is less than 1 upon square root m. So this suggests that if we choose delta equals to 1 upon square root m, we have done. So now you can verify that this delta actually works. We have the function fx equals to 1 upon x minus 3 whole square, and we have found given m greater than 0, we have found delta equals to 1 upon square root m. Let us verify whether this delta actually satisfies the condition or not. So the definition says that if mod x minus c lies between 0 and delta, then this implies mod x minus c is less than 1 upon square root m, because delta is equal to 1 upon square root m, and this implies if we just take the square, then we get x minus 3. Here c equal to 3, So x minus 3 whole square is less than 1 upon m, and which implies that 1 upon x minus 3 whole square is greater than m, which implies that fx is greater than m. So we have proved that for given m greater than 0, we have found delta equal to 1 by square root m, such that if mod x minus c strictly lies between 0 and delta, then fx becomes greater than m, and this proves that limit x tends to 3, 1 upon x minus 3 whole square equals to infinity. So the function is ln x. Let m greater than 0 be given. We have to find a delta greater than 0, such that when x lies between 0 and delta, fx is less than minus m. So that is, when x is less than delta implies ln x is less than minus m, which is true if and only if x is less than exponential minus m. So this gives delta equal to exponential minus m.